Is the presentation visible?
Yes, sir.
Okay. Today I had problem even before the start. My Chrome crashed. Sorry about that. So I have also, Showman has also shared this presentation through Moodle. So you can keep that handy in case we have problems in seeing the presentation. Okay. So we now move to a new module, which is the use of Lambda in C++. So we have looked at the Lambda syntax, semantics, and the typed Lambda calculus. Before we move further into type systems and the different forms of semantic representations of programming languages, we want to take a look at how Lambda is now getting in the under the skin of many of the strong programming languages. You have already seen languages which are based purely on Lambda, the functional languages like Haskell, Scheme, and so on. But the fact of the matter is, it is started playing a very strong role directly in languages like C++, where it has become an instrument to strengthen the language. Particularly, it was introduced in C++11. Lambda was not there up to C++98 or is corrected version as C++03, which took quite some time to get revised and expanded rather in C++11, and we have seen subsequent series of revisions or expansions of the language in terms of C++14, C++17, and very recently, that happened in December, we have C++20, which is the latest version of the C++ language. But in most of the compilers right now, C++11 and C++14 would normally be what will be available. From C++11 onwards, you have lambdas in C++. Okay, so to understand lambdas in C++, we need to first have some idea about what are functors or function objects. Even though you may be familiar to different extents with C and C++, you may not have really come across this idea of you know objects which can behave like functions. So those are called function objects or functors. So we will have a series of introductory slides which talk about how can we look at function from a little different perspective of objects and combine, basically have functions as a part of our object oriented language feature, and what are the different reasons of why you would like to do that. And then we will move on to writing lambdas in C++ and show that they actually are temporary functors in C++. Right? So first we talk about functors. So to understand functors, let us understand that these languages have something called a callable entity. A callable entity is an object that can be called using the function call syntax. So how do we identify the function call syntax? If I have a function factorial, we'll say the factorial, then we have a pair of opening and closing parentheses having one parameter. We can have functions which take no parameter, more than one parameter, whatever. But this pair of opening and closing parentheses is recognized as something which can be called, which is a callable entity, as it is said. So we very interestingly we now associate the operator opening parenthesis closing parenthesis as a notion that this is an operator which is a function call operator, that is which enables function calls to happen, right? And such objects are often called function objects or functors, right? So there are several callable entities in C++. Some of them are from C, some are new additions. Like uh, the what we have are macro, as we say, macro with parameters, which are function like macros. Then we have C functions in the global or in namespace. We have member functions, which can be static or non-static. We have pointers to functions, which have been classical ways to have function pointers in C. And we can have pointers to member functions, static as well as non-static. We can have a reference to function, which acts like constant pointers to functions. And we have functors, which are objects that define the function call operator. So there's a variety of ways you can actually make a call in C++. So function pointers, which is what you all know from C, are basically they point to the address of a function. So pointer is the address of an object, and we say that when you have a pointer to int, it is an address which is pointing to a location where an integer is stored. Similarly, when the object is a function pointer stores an address of the beginning of that function. So ordinary C functions can have function pointers that you all have seen in the PDF course itself. Then we have static C++ member functions, non-static C++ member functions. You can have function pointers to them. And what is a function pointer? It points to a function with a specific signature. To define a function pointer, we define a signature. So we have a list of calling parameter types. These are the types based on which the function pointer can be invoked. We have a return type, and we have what is less explicitly known. What we say is a calling convention. Calling convention, in one sense, what you would understand is based on whether you do call by value on a parameter or call by reference in a parameter, return by value or return by reference. This part of the calling convention you are familiar with, but there are certain hidden parts of the calling conventions which differ between C and C++. For example, C does not have overloading, so the function name itself is the callable entity in C. Whereas in C++, you can have overloading. So there could be multiple functions having the same signature, having the same name, but differing in the parameter list of the signature in terms of number of parameters or types. So naturally, they cannot be called just by the name. Their name needs to be kind of mangled with the information of parameter type in certain uniqueness and called accordingly. So that those are the factors which are part of the calling convention, which goes into somewhat of the implementation details of function pointers. Take examples. So this is how you define a function pointer. The name of the function pointer pt2 function, and it takes 3 parameters, let's say, returns an int. And to mean that it is not a function but a function pointer, we actually write the dereferencing operator star, right? So that says that whatever pt2 function points to is actually the function. This is a pointer. Now, in terms of calling convention, this is what we have commonly used, the function signature and the function body. Now, given a function pointer, we can assign a function which with matching signature to the function pointer. So do it is a function taking int char and returning int. So the address of that would be ampersand do it. I mean, that's a typical way we write address or the reference to a particular entity. So that becomes the address of the function, and it can assign it to the function pointer pt2 function having the same signature. But the interesting fact is, in terms of function pointers, since function pointers and the function itself is an address where it starts. So it also syntactic sugar is that you may just directly use the function name without the ampersand, and it means the same thing. I mean, these two are equivalent syntax. This is a special case of syntax. It will not happen if x is a variable of type int, then x will always mean the value, the r value, and ampersand x will always mean the address or the l value. But here, in case of a function, both of them actually mean the address. What else can you do? You can compare two function pointers for equality of function values and check what it points to. And you can call a function pointed to by the function pointer. So if you have done, say, pt2 function, if you have assigned to do it, then you can dereference pt2 function, and that will mean invoking do it with these parameters. So int will go as 12 will go as a, character a will go as b, and character b will go as c, and this function will do it, will get called, right? So that's a, so just a recap of the function pointers in C. So just side by side, there are two typical ways we have seen. One is you can directly have a function pointer, assign it, and then call it. The example just you saw in the previous slide, slide 7. We are in slide 8 now. Or what you can do, you can make this name a kind of a type alias. So you can do a type def on this, where this becomes kind of a name of the function pointer type. In that case, so in the left, pt2 function is a function pointer variable. On the right, pt2 function is a function pointer type. So now using that type, you can define a function pointer f and initialize it with, say, do it. And again, in a similar way, you can use f to invoke the function. So this is what is known in terms of C. Coming to C++, you can define a function point. Of course, whatever you can do in C, you can do here. What additionally you can do, you can define function pointers to member functions. So when we say this, a colon colon this, obviously we are in the namespace of class A, and we are meaning a member function pointer having float char as the parameter and returning a type value of type int. So now if do it is a member of class a member function of class A having the same signature, then I can assign the function pointer a colon colon do it, which is the address of the member function in the class, to the function pointer pt member. I can similarly check for equality, and I can invoke it, and obviously I need the object to invoke that. So the current object being this, I'm the pointer to the current object being this, I do start this, which gives me the object, and then I dereference the member function pointer pt2 member and put a dot to actually invoke that. So this is just a simple extension of function pointer in C++. So if we look at what can we do with function pointers, we'll say a couple of things. We can assign an address to a function pointer. We can compare two function pointers. We can call a function using a function pointer. We can pass a function pointer as an argument as well. We can return a function pointer, and we can define arrays of function pointers. So these the function pointer operator allows these operations to be done on function pointers. Right? Now, naturally, unlike the normal pointers where you could, for example, if p is a pointer to int and size of int is 4, and p happens to point to an element of an int array, then you could do p plus 4 to mean the pointer to the next element in that array, right? So you could do this kind of pointer arithmetic, or if you have two pointers pointing to two different locations of an integer array, p and q, two pointers to int, you could do p minus q, q minus p. This kind of an these kind of expressions are allowed in terms of general pointers, but obviously for function pointer, such arithmetic of increment, decrement, or difference would not make any semantic sense, so they are not allowed. So these are the things that you can do with the function pointers. So, what is the context in which function pointers are used? The programming techniques for which the function pointers have to be there is they can replace switch or if statement where you need to do different functionality based on certain information. We can realize user defined lead binding or functions in dynamically loaded libraries. We can do virtual functions in C++ using function pointer, and we can implement callbacks. So these are the contexts in which function pointers are used. We'll take one example each quickly because many of you would probably know this, some of you may not. So I'll just take one example each to show you what it means. So in terms of a switch, let us see what we are trying to do is given to look at the left code on the left, given to float values A and B, I have defined on top 4 different arithmetic operations, plus, minus, multiply, divide, and kind of I want to write a calculator, right? So in the calculator, if I do A plus B, then it should add. If I do A minus B, it should subtract, and so on. So what it means is once I know A and B, I need to call the appropriate function based on the operator that I have specified. So it's kind of a dynamic dispatch situation that we have. And C, as you know, does not have that kind of a dynamic dispatch. So one way I could do is I could write a function calling function. This is a function invoking function. I call it switch, which takes the two operators and kind of a takes a code for the operation that needs to be done. So I take a code either plus, minus, star, or slash. And then based on this code, I do a switch case. And depending on the case, if it is plus, I know that I am intending to add A with B. So I invoke plus AB to get the result. In this way, in any case, I'll get the result and then print that result. So this is a very, very usual C way of writing it. In C itself, I can write it in a different. I mean, I should mention that don't get confused that this is written with include IOStream and using namespace std. That is done just to simplify the input output streams. So this, I mean, what I'm intending to show is the C feature itself. This is completely otherwise completely C. I'm using the IOStream and a C++ compiler to compile just to make this. Printf would have been a lot more clumsy to write. That's it. Now, what other I can do is instead of actually sending a code and then switching based on that code and calling the appropriate function, I can actually pass the function pointer itself. So when I want to add, I will actually pass AB and the function pointer at the address of the plus function or the minus function. And this my function calling function switch becomes simply it takes the function pointer pt2 func, which is a parameter to this function, taking two floats and giving a float. So this is a third parameter. And in that, if I pass ampersand plus, which takes two floats and returns a float, then pt2 func is actually plus. So I will call pt2 func AB, and that will give me the result. So you can see that I don't need to do this switch. This function pointer called appropriately will by itself do a dynamic dispatch to different functions. So that's the basic mechanism of, instead of doing a switch or if, you could directly use the function pointers. That's a pretty much a C style of doing things. The second that I illustrate is late binding or dynamically loaded library. Dynamically loaded library, I'm not sure if you are familiar with the concept or with the requirement. The concept is, suppose why do you need dynamically loaded library? So let's say that you are compiling a C function. Now, while compiling a C function, you have used stdio.h. From stdio.h, you have used printf. Now, while you are writing your code, you simply include stdio.h, the header file, which just has a signature of printf. Whatever that signature is, you should open up stdio.h in your system and see what that signature is. Now, finally, when I link, that is with that signature, I can validate that the call to the printf is fine. But when I actually generate the final executable, I need the body of printf, right? Because I will need that body to be executed. So what I do at the link time, I refer to the precompiled source of stdio.h, which is stdio.c, which is already compiled and kept, which has the printed function and its body. And I include that compiled version of stdio.c as a part of my executable code. I physically include that and make this whole thing. So it becomes kind of one single executable a.out or .exe in Windows, and I can keep using that. So this is what is called mm, early binding or static binding. Right now, with this, what will happen? Now let's think, it is not usual, but let's think that we have created such a code, compiled and created my executable, say on today, on 3rd February 2021. Now, say 2 months down the line, for some reason, a bug was found and stdio.c was changed. It was compiled again by the library builder, and it was provided in the system. Now, since you have compiled the code with the earlier version, and the implementation of printf is already a part of your executable code, even though a corrected code has been provided, you will not be using that until you relink your code, until you recompile your code and relink with the new version of stdio.c. Right? So this becomes very inconvenient. So we often see that systems keep on saying that, well, we need to upgrade the system. There are some regular versioning that happens on the software systems, and you need to do upgrading, and then during upgrading certain things are downloaded, and then things work fine. Now, how do they work fine? Because if with this upgrading, if you have a new version of the library, then naturally you have new versions of the code. But how will your already built executables be able to take advantage of this new code? Because the library code is already a part of the code that you have already built, unless you rebuild. So if Microsoft provides a fix to the Word program, then the Word program will still not behave the way the fix is intended, because Word program has already built with the earlier part of the library, and that's a part of the Word executable, right? So to free free the programs from this binding, a concept of late binding or dynamically loaded library is introduced, where what it is done is very simple. When you link with the library, you don't include physically the code of printf in your exe. You don't physically include that, but you include a reference that this is the point where the code of printf will be called, and let the library remain as it is. So what happens when at the runtime, the system finds that there is a call to printf. The printf body is not a part of your executable, but it knows that it comes from the system. So it will use that system name and go and find out what is the current executable for stdio.c, current executable for printf, and call that. So with that, what will happen is that binding is becoming late. So what is happening is now if you change the library code in the system, when later you call it, when later you execute your program, even though you have not rebuilt it, since the code of printf is actually outside of your built code, the latest code will always get called. So this is what is the sense of dynamically loading. So what I show here is and this feature actually exists in C itself, because otherwise you would not have been able to build so many complex systems. So this is a special mechanism. So DL open, this is just one way to do that. In this is system dependent. So the way that is shown here is from Unix. So it says there is a special function. Again, that comes also as a part of a library. It's called DL function, dynamic library function .h. So that has a function DL open, which gives a name of the executable, where SO in Unix means shared object or dynamic library. So you give the name of that and some parameters. Don't worry about what that parameter means right now. It just says lazy, that is bind it lazy. So this gives you a handle to this hello.so object. And so using that handle, you then you have a type def of hello t. Hello t is kind of the function pointer that you want to use. You initialize that, you use that type to initialize your function pointer variable to null, and then you are actually picking up the function that you want to call, which has the name hello in hello.so. How do you get to hello.so? Because you have already got the handle. So you are doing DL sim, dynamic library symbol. So you're looking into this handle, which is hello.so. What are you looking for is a function called hello, and it returns you a void star, which is actually the address of the function. You cast that to the hello t, your function pointer signature, and you get your hello function in the current form. And then using my hello, you call that hello, and then you close the handle. So this is a simple mechanism. So in your actual in your program, you have just defined hello as an external symbol, because you are not providing the function body here, right? So for example, let me, I'm sorry. So this is the basic mechanism of dynamically loaded library or late binding. Now naturally, this could not have been done unless you had function pointers. So that's a big use of function pointers. Moving on, the other example of late binding, which is common in C++, which you all know, are virtual functions. So I have a class A having two member functions, F, which is non-virtual, G, which is virtual. I have a child class B where I have overridden F and G both, and provided, whatever the bodies are. And then I'm doing an invocation. I instantiate an object of A and an object of B. And then I take a pointer to the class type A and use the address of B. So if I directly call on A, F and G, I get the functions bodies in class A. But when I do P pointer F, even though P is a pointer to class A object, I dynamically it finds out that the object is B and actually calls the function of the appropriate type. So here, since F is non-virtual and P has a type of A, so P pointer F is statically bound because it's bound from the type of the pointer. So P pointer F still continues to call A colon colon F, even though you have overwritten F in B. But when you do P pointer G, it is virtual, so it is meant for let binding. So it calls the function that corresponds to the object that you are currently pointing to, which is object of class B. So it calls B colon colon G. This is a behavior common. I mean, this is the you know strongest behavior of inheritance programming in C++, which all of you will know, and you know that this is achieved in terms of virtual function table and so on. So that clearly shows that this kind of a late binding is possible only if you have function pointers playing their role. The last, which is very common in software systems, is what is known as a callback. A callback is, suppose you are trying to write a library, and in that library you want to invoke a function which you do not know. So you want to invoke the function, but that function will be known only in the application. So what he is saying that in the library, I'm writing a function pointer, say star func, and I call them as star func, but I do not know what that func is. Whereas in my application, I acknowledge that there is a func which is external, which means it is in the library. I have the function f provided, and I put ampersand f to func. So what will happen when in the library G is calling this function pointer, it will actually call f, right? So this is what will happen. I have invoked from main. I call G in the library. It goes here. In G, I have star func getting called. So when the control comes here, and what is star func? Star func is f in the application part. So it comes back to the application part. It invokes f. After f is done, it goes back to the library. This mechanism is called a callback, because the library is calling. I mean, normally you do call forward. You call from the application to the library. But here the library is calling back into the application. So this functionality of f, which the library is having to use, was not known to the library when it was written. So it calls back to get that, and then it proceeds, and finally the G gets back control to the application. So this is the whole callback mechanism. Step 1, calling G. Here, calling back into the application. Step 2, executing that function f. Step 3, going back into the library. Step 4, coming back here. Right. So this whole process of callback is been possible only if you have function pointers, right? So if you'd wonder that whether you have seen function pointers explicitly, yes, you can think about C library has a function given which is called the quicksort function. Now, the point is, if you want to write a quicksort function in general, which is a sorting algorithm, what are the things you need to know? You need to know it is a sorting on the array. So you need to know the element type of the array. You need to know how many elements are there. You need to know, given two elements, how to compare them, because the array could be of integer, array could be of float, array could be of structures, and so on. So everything kind of becomes unspecified in terms of the quicksort function. So this is the signature of the quicksort function. And look below, this is how you actually invoke it, where the particular instance I'm talking of is an array of 10 integers called field. So the first parameter you pass is a array. So how do you pass that? You basically, array address is a pointer, so you pass it as a void star pointer. So you take field, put it to void star, so base becomes a pointer to field. But then it will not know how many elements are there. So you specify how many elements are there. You specify 10. Then we will not know what is the stride, because it's a void star pointer. So it has no information on the size of the element. So you explicitly tell it the size of the element. What is the size of the element? Is int, which, so you say size of field 0, which is one component. So you give that size of, so it will know how to take the stride. And finally, you need to tell quicksort that what is the way to compare two elements? Now you cannot pass the element types here because there is no, there's no variable type here, there's no template in C and so on. So what you do is you pass two constant void star pointer. That is, you are passing pointers to two elements that you want to compare. Something very similar to what you do in swap. You pass that and you get a comparison result, which is an int, because you know that a comparison could be equal, could be less, could be greater. Three possibilities: -1, +1, 0. So, and you make that whole thing as a function pointer. So now you have to write a function pointer which compares two values of your intended type. So you get this. Now you want to do the quick sort on integer array. So you cast each one of that into integer. You take A, cast it to integer, and then dereference to get the value of that. Cast B to integer, get the value, and then compare as you do. And the comparison result is returned as int. So passed with two pointers to two array elements, this will compare them for integer by a function that you have given. So when quicksort was written, this comp function was not known. So what quicksort is actually doing, it is calling back into your application code to get comp func and actually be able to do this quicksort application. So there are several places where you need this. And for example, you want to write an integrator function. You want to write a function which integrates another given function. Now, there are several numerical ways to write integration that you will know. But how do you write that function unless you know which function to integrate? You will not know that. So you'll pass that function as a function pointer and do a callback in terms of its evaluation. Right. So this is the function pointer ways of doing this. But the basic problem with function pointer is there are quite a few issues. One is there is no value semantics. There is actually no value for a function pointer. It's just that address, which is. The type checking is very weak. You cannot do a sound type checking. More importantly, the next two function pointers having identical signature are necessarily indistinguishable. For example, if I have a function pointer taking one int and returning an int, then all functions that take one int and return an int are represented by that function pointer. I cannot have two different function pointers, each taking an int and returning an int. Type-wise, that is not resolvable. So that's a basic problem. Second is I cannot encapsulate the parameters. I mean, if I have a set of parameters that I want to call this function pointer with, then I have to, accumulate the parameters and make the call at the same time. I cannot have a memory in terms of having the parameters. Right? So maybe this is sounding a little Greek. As we go ahead, we'll know. So in this context, we define what is a function object or a functor. These are smart functions, which are functions with state. They have a state information. They can encapsulate C or C++ function pointers. They can use template. They can engage polymorphism. And every function pointer has its own type. It's a class with 0 or more private members to store the state. But the important factor is it must overload the function pointer operator opening closing parenthesis. This operator will actually execute the function. As it turns out, it is usually faster than ordinary functions. It can be used to implement callback and provides, okay, common design pattern we may not be doing. So what is a functor? Any class that overloads the function call operator. Be careful with the syntax. Like this name of this operator itself is operator opening closing parenthesis. Within that, there should be nothing because that is the identity of the operator. Like when you overload operator plus, you say operator plus, then put the parameters. So similarly, operator opening closing parenthesis called the function operator, and then you have another pair which says what is the parameters of this function that you are going to invoke. So these are different function call operator instances. So with this, now let us take a look at an elementary example. Here is a adder function, which is a classical function. Takes a and b, returns a plus b. Now I define a adder functor as a class where I overload the operator function with two parameters a and b and do the same thing. Now what happens? I have x, y, 5, 7 for actual parameters. I will invoke adder function x, y, and obviously that gives me the result. Now I instantiate adder functor as AF, instantiate. And then I call AFXY. This is a syntax you are not used to because it's AF is an object. How do I write this? Now what it actually means is AF, when you write this pair of parentheses, AF looks for an operator overloading in this class, which is function operator. It finds one. So it is, you are actually calling a dot operator parenthesis, taking parameters x and y. So it invokes this operator, passes x, copies x to a, call by value, passes y to b, call by value, computes these results and give you. So this is something. So what you can see is it is possible to define a class which has an operator, which is the function call operator, and you can make that objects of that class behave exactly like the function. And that is what is called a functor. So there are, if you look into STL, STL is full of such functors. So there is, so this is just a simple example of my class, which is what we have seen. My class has defined operator function call, and then you can instantiate and invoke on that. So for example, if you have defined a vector, I'm talking of STL code now. Now here you have rand, the random generator, as a function object in STL. And if you have defined a vector of 100 v, then you can use the generate algorithm, start with v dot begin, that is the beginning of the vector, go up to v dot end, that is the end of the vector, and at every point this will invoke this function object, which is rand, which means that it is actually invoking the function point. I show an equivalent of quicksort in C++ using the STL. So in STL, there is a sort algorithm which takes the iterator beginning v dot begin of a vector, iterator end v dot end of the vector, because it needs to know what to start, what to end, right? Mind you, here since we are STL users template, we do not need to pass the object by a void star pointer or pass its number of elements or its size of every element and so on, because being in template, I can directly refer to v, for which the type is known. So the compiler knows what is the element type and what is element size and so on. And the number of elements, I don't need to, I can actually, using this, I'm actually doing from beginning to end of the vector, beginning to end of the array, but I could use any sub array also. But what I need is a function which tells me how to compare elements, right? So that is defined as a compare function which takes two values and returns me a value. So that is what you guys see here, which is called a functional, which defines binary functions as a template. The first two parameters are binary functions. The first two parameters are types of the two arguments, and the third parameter is the type of the result. So using this template, you can instantiate any binary function. And then what do you want to do here? You want to actually invoke this function to compare, right? So you define the function call operator here with x and y, and then give the body. Since these are double, I'm just saying if absolute value of x is less than absolute value of y, right? So this that is how I want the comparison to happen. And this whole thing, the struct less mag, becomes a functor which can take two double values. I had lost connection. Can you hear me now?
Yes, sir.
Okay, okay. So, I mean, kind of coincided with the end of functor discussion. So, before we get into the lambdas, I would like to know if there is any question in terms of the, introduction to functor, because that is what will be heavily used in terms of the lambda in C. So, if there is any question, it is as such a simple concept, but it's just that maybe a little new to you that the function call itself could be thought of as an operator, and there could be an operator function which actually performs the call. But once you accept that mentally, then rest of it is very simple, that the function call is nothing different, but it could be just another object, another class, and instances of that could give you different function objects.
Sir, doesn't this function invoking of the operator is similar to the parameterized constructor?
No, the object is constructed once.
No, sir,
And
means the way the syntax in which we are calling the parameterized constructor is similar to the way we are calling this
no, no,
operator.
no, 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 no. The parameterized constructor you call when you are declaring that object at the initialization level.
Yes, we can't do that here, right? We can't do that
No,
here.
no, no, no.
Okay, sir.
No, there it still means the constructor.
Okay, means so we could have both in a class, right?
You will have to have, because unless you
Okay.
unless you can have a constructor, because I mean, once you make it a class, then it I mean, all properties of the class are there. So you could a functor class could have multiple constructors, but there is no confusion that can happen, because I mean, when you are constructing, it cannot be the function call operator getting invoked, because the object does not exist. So that will always happen with the declaration, where the type of that class or the class name will feature. But once the object has been constructed, then you, on that object, you'll be able to do this function call operator. And it is also, and that's interesting to note, that you could have overloading of function call operators. So one functor may have multiple function call operator functions based on the distinction of the parameter type. Right? I mean, you just keep on I mean, whatever you know about the class, just put all that here. Everything will work. Except the fact that now functions have a state. For example, I may not actually, here what I have shown is I'm calling this function with 2 parameters to add. I could make a version where I do not take any parameter in the function call operator. But I have 2 data members in the class where I set the values, and then whenever I call that operator, it adds the data members and gives me. So the 2 parameters I could pre-compute at some other point of time, and then when I want to add them, then I just call that add operator, but it does not take the parameters at that point of time. So it can have a state. So function calls now have a state, which you did not have as simple functions. Right? You're getting the difference, right?
Yes, sir. Yes, thank you,
Yeah.
sir.
Okay. So it's interesting. I mean, just try to. I mean, besides everything else, it's good fun. It's good fun programming. For example, here on slide 28, there's another example. I'm just trying to add the elements of a vector. Let's see how compact code can be written. So I use the algorithm for each. For each is an algorithm in STL which runs over a container from the starting iterator to the end iterator. So v dot begin to v dot end. And what it does, it applies the functor on every element. Okay. So I'm making use of that fact. And I have defined a functor adder here, which is a unary function. What it does, it takes a double and returns nothing. It internally has a data member sum, which at the time of construction is set to 0. So this is a constructor set to 0. Sum is 0. And then what does the function call operator do? Every time it gets a value, it adds it to x, adds that to sum. Sum plus equal to x. So what will happen when I invoke this? The first time I invoke, this gets initialized. Sum gets initialized to 0. The first v0 gets added to sum. Then every time I invoke, as I go on this iterator on the vector, every time I invoke the corresponding, the next v2, this function call object is called on v2. So v2 gets added to sum. Then function call object gets invoked on v3. v3 gets added to sum. So the elements of the vector will get added one after the other. And so when I AND, I have the result in the, so this whole thing returns the functor object. So that is a result. So I get result dot sum, which gives me this sum. This everything is struct, so everything is in public. So that gives me the result of this summation. Right. So this is how, I mean, this is programming in a very different way. I mean, it's not, you're adding elements of a vector but not writing a for loop. It's all doing everything in the conceptual way that for loop is nothing but an iteration, and adding is nothing but doing an operation with the element and an external variable. Okay, so that was kind of the functor. So let's now move on to our actual interest topic, that what lambdas can do in C++. This is an example which I had shown earlier also, but that was more just on the go. So just an example of lambdas in C++. What we show in this example, these lambdas are given below in the classical lambda expression that we have known. So twice is a lambda expression to apply f on v 2 times. We have seen this. Then I have a function f which adds 3 to the bound variable I. I have a lambda expressions for square, which squares the parameter. And I have again, this we had done at length, the composition of f and g on v. So it applies g onto v first and applies f on the result of application of g on v, the composition. Now we parallel and see that for twice what I need, so this bracket, pair of square bracket, indicates that I have a functor. I have a lambda here. That's kind of the signature of a lambda. Then I write the binding part of the expression. The first has to be f, second has to be v. And mind you, when I am in C++, so everything that I write, so I could have written this in more, actually I should have written this in more explicitly typed lambda calculus. So what I'm saying is v is of type int and f is int to int function. So this is again what comes from the STL component functional, which has a entity called function, the template called function, in which I can write the signature of a function in types. So within bracket it says int, the parameter is int, and it returns int. So this is how the function is written. I do not want f to be changed, so I make it constant reference. So that is f. So it's f to f, and v is. So what it does, it applies f onto v and then applies f again onto the result. So applies f onto v. This is simple thing. So this whole thing is this lambda expression now. Couple of things to note. One is we have not, in terms of this lambda expression, lambda in C++, we have not given a return type, right? Which is kind of mandatory in C++. So what you mean is in the style of lambda, as we have seen in the typed lambda calculus, in the style of lambda, if I have a lambda expression, typed lambda expression, then I can apply type checkers to find out the if that pre-expression is an expression. That is, I can find out what is the type. So the same thing is being done here. So it will find out that f is int to int, v is int. So fb, the function application, think about the type checker rule, will tell me that this is int. Then I am applying int to int on int. Again, the same type checking rule will tell me this is int. So this whole expression has this whole expression has a type which is int, which will be taken to be the return type. Similarly, the second one is actually simpler. You have a parameter lambda I, which is int, and you return I plus 3. Square is similar. In composition, you have two functions, both int to int. So you have f and g, and the third parameter, binding parameter, is v. And this is the invocation, which tells you that this too is int. And then these lambdas, so this and what you get, so if you see on the right hand side, what you are writing are kind of functions, but they are in the style of lambda. They do not have a name. They are unnamed functions, right? All of these are anonymous functions. But for our reference, we are defining a name to them. So it's kind of int x initialized 5 kind of notation. So this is the initializer. This whole initializer is actually a functor. And what is being initialized is an object of type twice, object of name twice. Right? So then this becomes a functor. So I can invoke it in the functor notation. I can take f, which Sorry, I had lost connection again. Is the slide visible now? Okay. So in the invocation of twice, you can see that the first parameter is also a functor, because this is what you are taking, a functor. So I pass f, and the second parameter is a. So what it will do is apply f on a twice. So a is 7. So it will add 3 to a twice. So it prints 13. Similarly, I could do the same thing using comp lambda by passing f to both of these composing functions, and I get the same. So there are different examples here, right? So this is that, I mean, just an elementary way, I mean, style of how you write functors. Now, what will be new to you is, and which was not there in C++03, is this auto business. So here you expect a type to be written. For example, here you would expect int to be written, right? And auto actually meant something different in C++03. Going from C++03 to C++11, that meaning has been changed. What auto now means is, when you are declaring a variable with initialization, if it is possible to know the type of the variable from the initialization, and if that is the type that you intend, then you can write auto. The type checker will deduce the type and put that type here. Right. So here it says that the a is initialized with 7. 7 is a constant of int type. So this auto actually will mean for a that a is of type int. But suppose you wrote a initialized with 7.2, then 7.2 is a literal of double type. So auto will mean that a is double. But suppose you wanted a to mean float. You want to say float a initialize 7.2, that you cannot do using auto. Then you will have to write float a initialize 7. If you write auto a initialize 7.2, then it will necessarily mean double a initialize 7.2. So it is kind of doing a type deduction here. So same thing is done in case of this. It's complicated to write the type of these functors. So what you do is you tell the compiler, okay, I do not want to tell the type. You process all this, decide on the type, and that is the type that you use. I'm happy with that. So that's the basic fundamental of what we have. Moving on slide 31. I'm taking another example again here using functor. This is a functor example, has nothing to do with lambda. So what I'm doing is I have defined a functor mod which has a data member modulus and a function operator, function call operator, which takes a parameter and returns the remainder of by that modulus. So it is doing a modulo operation. That is my function call operator. And I have modulus as a value, and here I'm hard coding that when I construct this functor, I hard code that modulus is set to 8. So it will always do modulo 8. Rest of it is just for illustration. So I have a vector in and out. In the input vector, I do pushback of 10, 25, 40, 55. 4 elements I have pushed in. So vector has 4 elements now. So the size of the vector is 4. So I set the output vector of that size. And then I do an iteration on the input vector to print it. So I do auto. Again, I do not want to write the whole cumbersome iterator signature. I do it as in.begin go up to in dot end, and every time you increment and you print that iterator content, which is the value. So it is 10, 25, 40, 55. The elements that I've inserted is, so this is the input vector I've printed. Then I want to apply transform. That is, I want to take the input vector and do the transformation as given in the functor and write the output vector. So I transform in begin to in end and start putting that transformation in the out begin, the output vector. And every time I use this functor mod, so what it will take? From the input vector, it will take element by element, apply this mod, that is a function operator doing modulus 8, and put it to the output. And then next two lines are writing that output. So 10 modulo 8 will be 2, 25 modulo 8 will be 1, 40 modulo 8 is 0, 55 modulo 8 is 7, and so on. So this is just a simple example, again, showing in the functor. Now we will write it in Lambda. Now using Lambda, I do not, again, back to slide 31. Struct mod this functor, now I will get rid of that. What I do when I was in the transform algorithm, when we're using that functor, there itself, I'm writing the Lambda. It's an unknown functor, unnamed functor object. What does it do? It takes an int, returns v percentage 8 because we had set modulus to 8, and this is a functor. So it applies this functor in form of Lambda on every element of the input vector and creates the output vector. So you can see that a lot of the syntactic stuff we had to write outside in the earlier case is simpled out, and I can just write it in situ here. Let's go to the next. This is what we wrote. This is the change. This is what top is in terms of the functor, and below is in terms of the Lambda. So you can see the compaction in terms of the code that you can get, and it gets simpler. Slide 33. Let us go to slide 34. Now what we do is we are no more hard coding 8. We have made that a parameter to the constructor, parameter m. And I have a global which is my mod, which I have initialized to some value. And then the functor is instantiated with this global value as a parameter, my mod. So it will still do modulo 8, but that it will that can be changed if I change this global variable. The same functor will do different things, which is as expected. Now look at carefully in terms of the Lambda. The parameter part is same. The return body part is same. Obviously, now I do not have a fixed value 8. So what I want is actually by the value my mod. So I give v percentage my mod. I also specify the return type, because from the functor, it is not possible to know the type of my mod. So I cannot, my type, this functor is not a type checked expression because I do not know this type. So I need to know that from the environment. So I specify the type. So this is how to do the return type, a very different kind of syntax. And then in the initial closing, in the initial square brackets, I put this. Mind you, think in Lambda terms. So this is Lambda v dot v percentage my mod. So what it means that v is a bound variable, which is a parameter, and my mod is a free variable. My mod is a free variable, which is outside the scope of this Lambda, which has to come from the environment, right? So that is what you specify here. you tell the lambda that, well, this is the v is the bound variable, the parameter, and my mod is what you'll get from the environment, which is a free variable. So when I run this in the environment, it this being 8, when this lambda get constructed in my static environment, mod 8 is, my mod is int. So the type of this becomes int. So it validates with the return type as int, and the value of my mod is taken to be 8. It does the same thing, but does in a different way using the lambda. Right? So this is how it is known in the simplest form of lambda syntax in C++. You have the parameter list, as you have seen, with types. You have the function body, and here what you have, the capture list. The parameter list and the capture list, any one of them or both of them can be empty. For example, this is a valid lambda. No capture, no parameter. You are writing hello world. So this is a lambda. This is a functor which can be used. So I can write, if you look below in slide 35, there's a capture, there's nothing, there's a parameter, nothing. I have the body, and this whole thing is a functor. So I can invoke it with a pair of parentheses. Right. Now, parameter list is just sequence of parameter types, variable names, same as the function, ordinary function. Function body is like an ordinary function. And of course, the function body can now have invocations of other lambdas and functors. If there is no return statement in the function body, like in the case of hello world here, then the return type is assumed to be void. That's what the type checker does. If the function body consists of only a return statement, which is very common, the return type is assumed to be the same as the type of the value being returned. That is the example that we saw earlier. So this is what we have. Next slide, 36. So this is the hello world lambda version of hello world in C++. So this is your lambda, and you invoke that, and it has a void type as input. It returns a void type as output, and this invokes, and side effect is it does a cout. Let's say another example. Here is I'm using a lambda in if comparison. If these are conditions, so this should give me boolean. So what? Let's see how it does. The capture list is null. There's no free variable. The two bound variables I and j. It returns 2 star I equal to j. So if the second parameter is double of the first parameter, then it is true. So this is my lambda. Naturally, the return tells me that the return type is int. I don't need to specify. And then I apply it on the pair 1224. Right on 1224. So this will give me, obviously, it's true. Another example where I specify the return type. So capture list is empty, no free variable, two bound variables x and y of type, each type return, returns a type int, and then a code which has different comparisons and return values. This whole thing is the lambda 43 xy are what it is applied on. Another example here. I have a single return statement. I take two parameters, both are double. I have a single return statement x plus y, but I have still specified the return type. If I do not Then from this, the type of x being double and type of y being double, x plus y is double. So the return type will be taken as double. And on application to 3.14 and 2.7, I will get 5.84. But if I say that the return type is end, then the lambda will return 5, quite obviously. Right? So I think these are simple ways to look at. So now the overall structure of the lambda expression. This part is called introducer. On slide 38, this is the part which is the introducer, which is saying that I have a lambda expression to start. Within the introducer, my mod is the capture variable, which in other words I can say is a free variable being set from the environment. The capture has that sense that you are capturing it from the environment. Then you have parameters here. Then you have the return type, next, optional. Then you have the declarator, parameter arrow return type is called the declarator. Then the whole lot of statements, the body of the lambda, and the whole thing is the lambda expression. So this is, so now we'll see different variants of what all can go in here. So this lambda expression is called a closure object. This does not have a name. Right? So anything in compiler that does not have a name becomes a temporary object. For example, I write x assigned y plus z. Y has a name, it will have an address, it will have a value in that. Z has a name, has an address, has a value. Y plus z. This expression does not have a name. So how does the compiler deal with it? It creates a temporary object for y plus z, where the value is computed. And then that temporary object is assigned to x. So it's exactly the same way, except that now this object is a functor. The lambda expression is a functor, which is called the closure object. So the evaluation of this results in a temporary object called the closure object. Obviously, the closure object is unnamed, and closure object behaves like a function object. Right? Examples. So closure object, this is your capture list is empty, your parameter list is empty, and we have seen this kind of example before also, prints 4. Your capture list is empty, but your parameter list is v, and you are doing v times 6. This whole lambda you're applying on 7. So this is the output. I have a global here, which is I initialized with 7. I have a parameter list which is v passed as reference to int. And since it is a reference, it can be changed. So I apply it on I, which is 7. So it will turn out to be v assigned. So I'm applying it with I. So it will be I times 6, which is 7 times 6, which is 42. So now this prints as 42. I'm slowly taking examples of simple to more less simple. Now, again, I'm going back to slide 40. So remember this int ampersand v and v star 6 I. Now the change that I make is I make this v const and try to write the same thing. Obviously, I'll get an error now on this lambda because v being a constant reference cannot be changed. I cannot do an assignment to v. So this lambda will not work. I do this. Obviously, this will work. I'm applying it on j. J is 7. Look carefully. We are doing some cluttering with the namespace. I have a global variable j initialized to 7. I have the parameter list v as reference and a parameter j by value, and I'm doing v star assigned j. I'm invoking it on j6. Now, mind you, obviously this j inside the function body is the parameter j, and this j on which you are applying is the global variable j. This j on which you will print is the global j. So what happens? This is applied on j6, which means v becomes the reference to j, which is global. V becomes a reference to j, which is global. And this j, which is a parameter, second parameter here, is by value. So this j gets value 6. So this actually becomes global j star assigned parameter j. But Lambda can clearly differentiate the two because from the context it knows which is what j. So v is a reference to j. So when it does this, actually v changes, which means actually j changes. That's the reason when you come out of the Lambda and you print j, where you are printing obviously the global j, you get 42. Right? So Lambda's parameters do not clutter the namespace, do not affect the namespace. Lambda expression without a declarator acts as if it were null. That is, it is possible not to have a declarator, not to have any parameter indicator also. So even then it will behave as if there was one which is empty. So the capture is actually meant for capturing the values of free variables from the environment. So you have seen this MyMod example. Putting in terms of Lambda, this is what we have seen. Now the question is, when it is of parameters, we know a parameter can be by value, it can be by reference, and different parameters may have different parameter passing mechanism. Interestingly, a similar concept exists for the capture list as well. We can capture everything by reference. We can capture everything by value by default, or we can specifically capture different capture variables by different convention. All of these are possible. Let's see, 45. So in the capture list, if I just write ampersand, that means anything that I capture within the body will be by reference. If I write equal to symbol or assignment symbol rather, then it will mean that anything that I capture in the body of the function will be by value. And I can do specific, like I can just write identifier. So this is by value. I can write ampersand identifier. This will be captured by reference. I can do something like foo, ampersand bar, gorp. So foo and gorp would be by value and bar will be by reference. I can mix with a default also. This says that by default it is reference, but identifier will be by value. So all different ways you can capture and set the way you want to deal with the free variables. So let us try another Lambda. Int total elements is a global variable initialized with 1 for each. So I'm applying this Lambda on a container, cardinal begin to cardinal end. And what I'm trying to do is I'm trying to do this by doing total elements into equal to into assignment I, where I is a parameter. So which will mean that this will apply on each element of cardinal, this will apply the lambda. So for every element, cardinal 0 will be first taken, cardinal 1 will be taken next, cardinal 2 will be taken next, and you will get a product of all the elements of cardinal initialization. Naturally, for this, I need the capture to be by reference. And mind you, I have not specifically said total elements. So how does the lambda know that it has to capture on this? Because this is a free variable. Right? I is a local variable, so this is a free variable, so it has to be by capture. And that capture is reference, so I can change it. This is allowed. But if I had written this lambda with an assignment symbol here, then I'll have an error because then the capture is by value, which means that I can only read the value of total elements in the lambda, but I cannot change that. So I will not be allowed to do this. Or if I do not write any symbol, then also this will be an error, because if I do not say what is the type of capture, whether it is by value or by reference, then I cannot capture total elements by default. I cannot implicitly capture this. Either I have to say total elements here, or I have to say that I'm capturing everything by reference, or I have to say I'm capturing everything by value. Certain matters of syntax, but if you practice a little, if you think a little, you'll find that they're very, very straightforward. Yet another example of filling a vector. So fill, this is written as a operation on a vector where template T, you can easily see that T has to be a functor type. So every time you do a pushback, you check whether the functor is giving you true or false. Right? And this is how we invoke the functor. Given the vector of vector stuff, I pass the vector stuff, and then I pass in done, I pass a functor which says the stuff dot size is greater than or equal to 8. Right. So what I'm doing is, if I keep on doing this as I do this fill, what it will do, it will enter and it will start invoking this lambda one after the other. Every time it invokes, a pushback happens. Pushback changes the size. So when 8 elements have been inserted, then this lambda will return true. And this while loop will break. So this will simply insert 8 elements in the increasing order of the value of I. Mind you, the capture has to be by reference, because you are making change to the, by doing this, you are making changes here. You can do call by, you can capture by value also. I'm doing the same thing here, the same fill, but I'm using a different functor. I'm using a different lambda. What I use is I do an iteration on the elements of the vector and add them, something which I did before. So I basically, when I fill, I add this and I check whether that sum is greater than or equal to 0 or not. So I keep on filling till the sum exceeds 10. Now for doing this, naturally, my bound variable is I and my capture variable is sum. So I need to make changes to the sum. So it needs to be captured by reference. If I capture by value, it will be an error. Quite obvious. By default, you can capture here by value. This is just trying to compute the mod. It's not changing my mod, so that will work fine. And so on. I think there are quite a few examples that are given here, which I will not go through anymore. You can just go through, actually practice them on the system to get a better idea of. But it is just, these are just illustrations of what we have already specified. For example, here are some of the capture restrictions, like every identifier must be listed once. So this is fine, but the third one is not fine because we are writing Z twice. Default by value, explicit identifiers by reference. It's okay. This is bad. The default is, so it is already by default, it is default by value. So there is, you cannot write a simple variable here or simple value here, which is by value. It's kind of redundant, so it gives an error. For example, this is default by value. This is allowed by reference, but Z will not be allowed because we are again saying it's by value. Similar things for reference, right? So you go through all that, try them out. I will close with two interesting examples. Finally, no class on programming or no discussion on programming can end without factorial being discussed. So here is the factorial lambda. So what is factorial? Factorial is a function which takes an integer and returns an integer. So from the functional, this is my fact. And what does it take? It takes an int n. What does it return? It returns an int. This is if n is equal to 0, then it is 1. Otherwise, it's n times this. So when I do this, n is a free variable. N is a bound variable, and fact is a free variable. Right. So very interestingly, we have seen that when we had to do factorial in terms of the lambda expression, we had to actually create the corresponding y combinator. And then as a fixed point of the y combinator, we got this function. So all these are inside this. But in the lambda syntax in C++, things have been made simplified, because this is the name of the lambda itself is treated as a capture variable here. So the name of this lambda, which is fact, is treated as a capture variable with a reference so that you can make change. And since it is a functor, you can make use of it to call fact n minus 1. So this is a beautiful line which shows finally that how all this exercise of y combinator and fixed point can be put together in a very simple, sweet, compact notation in C++ lambdas, and you can make effective use of all that. I mean, once we have done factorial and Fibonacci is just a matter of writing a couple of more lines. So Fibo is the same way, and you can do that here. This is the capture variable Fibo, so you can use the capture variable as a functor here, and rest of it is the same. On slide 83, just showing that it is, you can explicitly write currying. You can do currying, because if you have lambda, you'll need currying. So I have auto a lambda which is of xy returns x plus y. I do another lambda add 5 capturing by default by value int y. Add, what are we capturing? We are capturing add, right? And by value, because we do not make changes, want to make changes to that. And then add 5y. So this functor gives me a new functor in terms of this lambda, which is 5 plus y, which is the curried version of this. So then I can do 5 plus 3 either by the original 2-variable function or by the curried one. Right? So note on the curry line we can capture also by default by reference, by ampersand add or add. Any of these will actually work because we are just using the value. Okay. And then finally there are a lot more of examples on lambdas in C++. So let me stop here. If there are specific questions, let me take. Otherwise, uh, this is a matter of quite a bit of practice that you need to do and quite a bit of fun programming which you can resort to, and actually gives you a really mm, I mean, besides making your deeper understanding in terms of programming languages through this course, if you intend to become a really efficient C++ developer of modern times, using the modern C++ in its full power, then this will give you a good starting point to get get to quite a bit of part of the C++ 11, 14, 17, and so on. Of course, there are several other features also that you'll have to master, like the move semantics and so on. But this is something which is very core to the whole thing that was kind of very synergistic to our discussion. So I chose to discuss this before we go into the type systems, where some of these glimpses will come back as to all these inferences that we are saying that the compiler will do. What would be some of the possible ways of doing those inferencing? Okay. Any questions? It was too heavy, is it? I don't know. There's less attendance also today. A lot of people missing. Anyway, if there is no further question, then let us close here today. And on next Monday, we will move on to the next module, where we'll briefly start talking about the type system. Meanwhile, assignment 3 will also be released today. Shoman, you have not released it yet, right?
No, sir.
Okay. So we'll confirm and release it today. Okay. Have a nice day and nice weekend. See you on Monday again.